Stars. Stars are large balls of gas held together by gravity that produce tremendous amounts of energy, which is what makes them shine. The sun is our closest star. Stars form from a cloud of gas and dust, which is called a nebula. This cloud of gas, like you see in this picture, eventually starts to spin. Maybe just something hits it just slightly off, and it starts to collapse inward on itself, spinning and heating up. Eventually gets hot enough for fusion to take place, and a protostar, the baby of a star, is born. In the star's core, two hydrogen atoms. In this picture, it's deuterium and tritium. These are two types of hydrogen. Deuterium has one neutron, tritium has two neutrons. They collide and fuse together to make a new helium atom, releasing huge amounts of energy, making the star expand. Nuclear fusion is the combining of the nuclei of smaller elements to form the nuclei of larger elements. Some of the mass is then converted to energy. For instance, hydrogen plus hydrogen, they each have an atomic number of 1, meaning they have one proton inside. When they are fused together, this produces an atom with 2 protons inside. Thus, it's now called helium, and it releases insane amounts of energy. Fusion is much more powerful than fission, the splitting of energy, which is what takes place in a traditional atom bomb. Fusion is far more powerful because, again, you are messing with the energy inside an atom. But what's really cool is this happens not just with hydrogen, 2 hydrogens making helium, 1 plus 1 equals 2. This happens on a larger scale. Here we've got hydrogen. Hydrogen has an atomic number of 1. You add a 1 plus a 1, you get a 2, which is helium. If you take 2 heliums, like in this picture, they form beryllium, number 4. You add another helium, and you get carbon, which is a 6. You could add another helium to get oxygen, another one to get neon, another one to get magnesium, and so forth, all the way down the line. This is actually how all of this periodic table, except for the human-made elements down here that don't exist in nature, this is how they were formed. What's even cooler is that iron, right here, number 26, this one is so powerful, it takes so much energy, it actually, when 2 atoms combine to fuse to make neon, God, I'm losing my mind. When they fuse to make iron actually sucks in energy, and so the whole thing collapses, and there's a supernova, and that's all that makes all of this. So all of the things iron in our blood is actually made in a supernova. Carbon, nitrogen, oxygen, these are common on Earth. These are all made in stars. So everything on Earth, all of these elements other than hydrogen, were actually made in a star. So our bodies and this planet are made of star stuff. We're stardust. Kind of cool. Now, inside a star, there's this constant balance between the pressure exploding outward with all this incredible fusion energy and the gravity, which is collapsing this inward, collapsing the star inward. When these two are equal, the star stays stable. But if one or the other is increased for some reason, or usually it's the pressure. If the outward pressure increases, the whole place increases, expands. If the pressure stops for some reason, fusion stops, it collapses. Typical star composition is primarily hydrogen and helium. You can see here 71% of a typical star is hydrogen, 27% is helium. And the rest of the periodic table are in smaller amounts, but all of these are made in stars. So again, oxygen in our blood that we're breathing, carbon in our bodies, nitrogen in our bodies, silicon in our glass, all of these things are actually made in stars. This is the life cycle of a star. They all start out the same. It's a stellar nebula, a cloud. And then if they are the size of our star, they follow this route. If they are much larger, though, they go this route and end up as a neutron star or black hole. All stars then originate from clouds of gas and dust. When the clump reaches about the size of Jupiter, It creates enough energy by nuclear fusion to shine, becoming a star. Jupiter, if it was just a little bit larger, would be a star. So it's actually what we call a failed star. If we're just a little bit bigger, we would have two stars in our solar system. When we're looking at stars, we use the term brightness. Luminosity and absolute magnitude are the brightness of a star. They depend on size and temperature. Bigger or hotter is brighter. And they all are complete absolute brightness or magnitude because you pretend that they're all the same distance. If you put them all the same distance, how bright would they look? Apparent magnitude is how bright a star appears to be for an observer here on Earth. Closer appears brighter. This is why the sun seems so bright. It's closer, even though it is in reality not very bright as stars go. It's just closer. So its apparent magnitude is very high, whereas its absolute magnitude is much lower. Distance is vitally important for apparent magnitude. Different types. The main type of star is called the main sequence. Thus the name, the main sequence. 90% of stars are here in the main sequence, including our sun. It's the majority of the star's lifetime, typically about 10 billion years for one the size of our sun. Our sun is about halfway through that. In this time period, they use up their hydrogen and helium, producing some of the heavier elements. And the length depends upon the amount of fuel. If they have greater amount of fuel, they burn faster and die faster. Picture a Hummer, the supersized car. It's much larger, has a bigger gas tank, but it burns through that gas really, really, really fast. Same thing happens with the larger main sequence stars. So they die, so to speak, very quickly. A giant or supergiant is the next stage. At this point, the star has used up most of the hydrogen, so the energy produced can't counteract the force of gravity. The core collapses and the outer layers expand. Giants are low temperature, high luminosity. They're cool, which would make them dim, but they are so big they appear very bright. They're usually red, orange, yellow in color, and they're older. Supergiants, which our sun will never be, our sun is not supersized, are very, very bright because they are so big, and they explode into supernovae. So here's the sequence so far. They both start as nebula, and then main sequence, and then our star is going to become a giant. Larger ones will become supergiants. The next stage for our star, after red giant, is white dwarf. Any star that's less than 10 times the mass of our sun will end up as a white dwarf. The outer layers from the red giant dissipate, leaving only a small hot core. When the last little bit of fuel is finished, it ends up as a black dwarf, a dead star. White dwarfs, though, are so small they appear very dim, even though they are very hot. Supernova, though, is if it's more than 10 times the mass of our sun. And I love this phrase, cataclysmic collapse of a massive supergiant, creating an intense explosion. Thing is that iron, like I mentioned before, when you start to fuse iron, it actually doesn't emit energy, it sucks in energy. So what happens is that the outer pressure, it no longer is producing any outer pressure. It's no longer exploding outward. This pressure dies. So the pressure stops, and the gravitational collapse begins, and it produces an incredibly bright light. Some supernovae have been known to be brighter than entire galaxies. There was one supernova that there were drawings taken of in the 1600s. It was so bright you could see it during the day, even though it was incredibly far away. So imagine a star suddenly become so bright we can see it when the sun is up. That is truly a bright supernova, and astronomers are dying to see the next one happen. So they start out as a nebula, become main sequence, our star will become a red giant, and then end up a white dwarf. Larger ones will be supergiants, and then supernova. They go the super path. Those supernovae either become a neutron star, if it's 10 to 20 times the mass of our sun, or a black hole, if it's 20 or more times the mass of our sun. Neutron star is when the collapse, the gravitational collapse, becomes 6 to 20 kilometers in diameter. So it's something more massive than our sun. And our sun can fit 1,000,000 Earths inside. So it's more massive than our sun, suddenly shrinking to something about the size of Washington, D.C. That's incredibly dense. It's so dense that 1 teaspoon of a neutron star would weigh 100 million tons. I can't even imagine that. And occasionally these neutron stars spin and become a pulsar. They emit this bright light and it pulses as it spins, and that spinning can be several times a second. Black holes are the other really cool things that supernovae can become. They implode and they don't shrink to something just 6 to 20 kilometers in diameter. They shrink even further, and they become so incredibly dense they pull not only matter towards it, but light towards it, which is why it's called a black hole, because you can't see it. Light itself is sucked towards it. So this is the final life cycle of stars. They all start out the same, but the smaller ones like our sun end up as white dwarfs, and the larger ones end up as neutron stars or black holes. Here you can see it again, separate. Now when our sun finishes its main sequence, like I said, it's about our sun is about halfway through the main sequence stage. Be another 5 billion years, it will become a red giant. At that point, it will expand to the point where it will swallow up the orbits of Mercury, Venus, and Earth. So if we plan on surviving as humans more than 5 billion years into the future, we need to find another solar system to live in. After about 50,000 more years, the outer layers will collapse, and it'll end up just the core of a white dwarf. Some relative sizes. Now, the supergiants you can see here are so much larger than our current sun, even larger than the red giant we will become. Because even though they are large, they aren't necessarily more than 10 or 20 times more massive. There's a lot of this is less dense in some places than our sun currently is. But you can see the distinction in size. And again, the life cycle. The Hertzsprung-Russell diagram groups stars by temperature and luminosity. It's also called the HR diagram. This is named for the two astronomers who came up with the diagram. Here it is. It's a graph. They just graphed stars by temperature along the x-axis and luminosity or brightness along the y-axis. They listed the sun as a luminosity of 1. So anything with a luminosity of 1 is exactly the same brightness of our sun. Anything on this line is 100 times brighter than our sun, like Aldebaran. It's a little bit more than 100 times the brightness of our sun. Anything along this line is 1/100th the brightness of our sun. So Procyon b, it would take almost 100 of Procyon b to equal the brightness of our sun. The larger stars are at the top, so because they are brighter, the supergiants. The smaller stars are along the bottom because they are dimmer, the dwarfs. If you notice, the temperature is a little odd. On the left it's 20,000, then it goes 10,000, 5,000, 2,500. The temperature actually decreases as you move to the right. So the hottest stars are to the left. And if you notice, the color depends on temperature. The hottest stars are actually blue in color. Yes, that is the opposite of your faucet in the bathroom. But actually, it is true. The hotter it is, the more energy it has, and the more towards the blue side of the spectrum it is. Cooler stars are red, 2,500 degrees red stars. they are relatively cool. Our sun is a yellow star, so it's a little hotter than the coolest. Our sun currently is here in the main sequence. It will expand, become brighter, but a little cooler to become a red giant, and then it will shrink, warming up and becoming dimmer to become a white dwarf. So as you move up the diagram, objects become brighter and larger. As you move down, objects become smaller and dimmer. Moving to the left, the temperature increases, and moving to the right, the temperature decreases. Now, how do we study the stars? As we've said before, we haven't been there. We can't measure them in person. So we study the light. This is called spectroscopy. Study of light, breaking it into the spectrum and analyzing the result, giving us the physical properties of a distant object. It tells us the composition, what elements make up a distant star. It tells us the temperature, the mass, the brightness, the movement. Remember, every element produces its own fingerprint in the spectrum. So if we know what a fingerprint looks like for a particular element, if we see that fingerprint in a distant star, we know that that element must be in that distant star. Here's the electromagnetic spectrum again. To the right is the high frequency, high energy, short wavelength of gamma rays, X-rays, ultraviolet. To the left, these are the radio waves. Low energy, long wavelengths, red. If it's moving towards us, the wavelengths bunch up and it moves in color towards the blue side of the spectrum. As it moves away from us, the wavelengths are stretched out and moves towards the red end of the spectrum. We discussed this with the Doppler effect. Spectroscope is the tool we use to study the light. Light enters and is split into the different colors by diffraction grating, like a prism. And then you can see the fingerprint. These are some sample element fingerprints: hydrogen, sodium, helium, neon, and mercury. This here is light from an unknown star. You can see that since this pattern exactly matches this pattern, it must have neon in it. The rest of the pattern matches Mercury. So this unknown star contains both neon and Mercury.